Ok, siete in 5, 3, 2, 7. Ok, iniziamo allora. Okay, so last time we started entering into the details of the weak interactions. We showed how experimentally it was proved that parity is violated in weak interaction, and this makes a huge difference with respect to QCD and QED. And this difference has to be properly taken into account in the way the interaction is shaped, and so in the way the current, the charge current in particular discussed, have to be formalized. And we found that the best way to encode parity violation and weak interactions in a formal way is through this B minus A formalism, okay, which essentially tells us that the proper way to describe the current in a QED vertex, in a charged current QED vertex, is as a mixture of a vector current and an axial vector current with the maximal parity violation, so with the B minus A, okay, a vector minus axial vector, and then we derive also the current for different QCD weak interaction vertices involving either particles or antiparticles. So now let's continue into this discussion. Let me first of all introduce the concept of Lepton universality, which will be, of course, necessary for the rest of this part. So let's consider the Moon decay. Okay, so we have drawn already this diagram several times in the last week. So we have a muon that transforms into a muon neutrino with the emission of a W boson, which eventually decays into electron and electron antineutrino. And here we can immediately identify two vertices. Okay, the first one is the muon into neutrino W, and the second is the decay of the W into electron neutrino. Now, in principle, so staying general, there is no reason to assume that the coupling of these two vertices have to be equal. Okay, so let's assume that they are different. And so we can write down now the decay rate for this decay, for the Moon decay, by making use of the Sargent relation that tells us that this decay width, or the inverse of the decay time, has to be proportional to the fifth power of the energy available in the decay, which in this case is just the mass of the muon. So we have a muon at rest that decays, so the total energy is essentially given by the mass of the muon. We can neglect the mass of the electron and the neutrino, of course. So by making use of the Sargent rule, the decay width for the muon can be represented in this way. So we have the couplings at the two vertices, the electron vertex and the muon vertex, so GFE, GFmu. Then we have the fifth power of the energy available, so the mass of the muon, and then we have some constant. And so lately we can invert these to extract the decay time of the muon, okay, in terms of all these quantities here. Let's now consider the decay of the Tau Lepton. The Tau is essentially a replica of the muon and of the electron, but with a much, much higher mass. The mass of the Tau is order 1.8 GeV, so almost twice the mass of the proton. Okay, and being so massive, it is allowed to decay in many more different modes. Okay, so not only in the electron mode, which is the same as the muon, as discussed before, but also in the muon mode. Okay, and also in mesons, so quark anti-quark systems. Okay, that hadronize into mesons. So given the large mass of the Tau, it has the possibility to decay in many more different modes. And so when calculating the decay time of the Tau, or the total decay width of the Tau, one has to sum over all possible partial decay widths for all possible decay modes, to the electron, to the muon, and to, in general, to mesons. This can be pions, can be kaons, in case you have an S quark here, etc. Now, let us consider, first of all, that since the mass of the electron and the muon are both much smaller than the mass of the Tau, okay, so we can in principle, in first order, neglect those two masses, then one would expect that the decay width of the tau into electron and of the tau into muon must be approximately the same, okay? Apart from a small kinematic factor which accounts for the different masses of electron and muon. But this is not the case for the decay into quarks, okay? Because here we have an additional 3. We have an additional factor 3 which accounts for the fact that since your tau is colorless, of course it is a lepton, then also the final state must be colorless. And so there are 3 possible ways that a quark-antiquark pair is colorless. So red anti-red, blue anti-blue, green anti-green. Okay, so you have to account for this with the factor 3. Now, let's write down now the branching ratio of the tau decay into electron. So the same decay mode that we discussed already for the muon. Okay, you see here the diagram. Again, making use of the Sargent rule. So the branching ratio is by definition the partial decay width divided by the total decay width. Okay, and the total decay width is the inverse of the decay time, the lifetime. Okay, and now we can express this partial decay width by making use of the Sargent rule. So this time with the 5th power of the tau mass. And then we have the 2 couplings, which are the electron coupling at this vertex here and the tau coupling at this other vertex here. Otherwise, the structure is the same that we have as the one for the muon that we saw in the previous slide. Okay. And so now we can again invert these and extract the decay time of the tau lepton. Okay, in terms of all these objects here and the branching ratio for this specific decay mode. Okay, and now we can simply compare the two. Okay, so we have the decay time of the tau lepton and the decay time of the muon. The difference is that for the muon, the branching ratio is 1. Okay, it is 100% probability to decay into electron. So it's just 1. In this case, we have to take into account this fractional probability to decay into this chunk. Okay, and the structure otherwise is the same. Of course, here we have G tau, here we have G mu. Now we can take the ratio of these two expressions. Okay, so essentially we can take the ratio of the two decay time, which corresponds to having the ratio of the two couplings for the muon and the tau. And this you see in the next slide. Okay, so you take the ratio, invert the formula, and so you obtain a formula now for the ratio between the coupling of the tau vertex and the coupling of the muon vertex. Okay, as a function of all the other quantities. It is the 5th power of the mass ratio, the ratio of decay time, and the branching ratio for the tau into electron. Okay. Now we can put the numbers into this formula and see what happens. So, let's start to calculate this ratio of couplings. So the numbers we take from experiments. So we know from experiment the branching ratio for the tau into electron is 0.18 or something. We know the mass of the muon tau. We know the decay time of the muon tau. And once you put all these numbers all together, this formula, you obtain that the ratio of the two couplings, so at the tau vertex and at the muon vertex, is essentially consistent with 1. Okay. So the coupling for the tau and the mu is the same. What about now the electron? So we can repeat this procedure, of course, taking into account the muon and the electron by making use of different channels, and again, you find that the ratio of the two is consistent with 1. Can anybody mute the microphone, please, at home? Now, so let's now put everything together. Okay, so what we found is that we must conclude that the coupling, so the charged current with coupling for the electron, the muon, and the tau must be the same. And this is what we call Lepton Universality. And this is indeed a precise prediction of the standard model. Okay, according to standard model, the charged current with coupling has to be the same for all 3 lepton vertices. But let me put a but with dots. Something happened this year, actually 2 months ago. Actually, this is the most recent result over many years of research, also in different channels. Okay, so with this paper, which was published by LXCD just in March, it appears that something is cracking in this Lepton universality assumption. So let me just go through the abstract of this paper. So the standard model of particle physics currently provides our best description of fundamental particles and their interactions. The theory predicts that the different charged leptons, the electron, the muon, and tau, have identical electroweak interaction strengths. Previous measurements have shown that a wide range of particle decays are consistent with this principle of Lepton universality. Okay? However, these articles present evidence for the breaking of Lepton universality in beauty quark decays with a significance of 3.1 standard deviation. So 3.1 standard deviation is not far, 5 standard deviation where you can claim discovery, but it is a level where you can claim an evidence. Okay, so can still be statistical fluctuation, but can also be something new. So, and these results are based on the proton-proton collision collected at the Large Hadron Collider. Now, the measurements are of processes in which beauty meson transform into strange meson, so kaons, with the emission of either electron and positron or muon and anti-muon. Okay, so in the final state, the only difference is that you have electron in one case, electron positron, and muon anti-muon in the other case. And if confirmed by future measurements, this violation of Lepton universality would imply physics beyond the standard model, such as a new fundamental interaction between quarks and lepton. Okay, so this is really something fundamental, something extremely important. Okay, we have a first significant evidence of violation of Lepton universality, which can be true, so due to new physics, or which can be fake, just due to statistical fluctuation. We need more data, more statistics, of course, to either confirm or reject this idea. So what did they measure in this paper? In this paper, they measured the so-called RK factor, which is essentially the ratio of the branching ratio of the B meson into K plus mu, divided by the branching ratio of the B meson into K plus electron positron. Okay, and then the two are normalized with some normalization channel. Okay, but the essential point is the ratio of the two numerators. Okay, and you can also see here the process. So we have a B plus meson, which is a UB bar meson, so a heavy meson, decaying into a K plus US bar, and then a pair of leptons is emitted through a kind of neutral current process that we will study later. This is, as you can see, there are many vertices, so this is not a first order diagram. It is a higher order diagram. And the reason for this will be clear today, later on, because the so-called flavor changing neutral current process are forbidden in the standard model at first order, at 3 level. They can only be possible at higher order, but this will come back later. So this is what they measured. And you see now the results compared with also previous results by the Babar and the Bell collaborations, which are E+E- experiments. So here the uncertainty was very large. The dotted line corresponds to the expectation from the standard model. Okay, so the first two were consistent. And now LXCB started to accumulate data. So the first measurement was with 3 inverse femtobar of integrated luminosity, then 5, and now finally 9. Okay, so the full statistics collected so far at the Large Hadron Collider. And so this is the experimental point, okay, the one that is published here. And in fact, there is, if you compare this with the standard model prediction, a discrepancy of 3.1 sigma, okay, which can be, again, statistical fluctuation or can be something new. So maybe one can interpret this process in a different way, okay, including a new exchanged object, a new exchanged boson, which, for instance, could be a leptoquark, where leptoquark is an hypothetical, for the moment, color triplet boson that carry both lepton and baryon numbers and can interact both with quarks and leptons. Okay. So this is a pure hypothetical object, okay? There is a theory behind this, but it is only theory, there is no experimental proof. But if this result is confirmed, this might explain, okay, with new physics, so something not explained in the standard model, why this Lepton universality is violated, if any, okay? Now, we close this parenthesis, okay, this is just a flash of something really new on the market, and let's, for now on, consider Lepton universality as a truth, okay? Now, having said that, let me now describe you an interesting feature of the pion decay, the charged pion decay. So charged pions are the lightest hadrons, 140 MeV, and so they cannot decay into lighter hadrons because there are any lighter hadrons beyond them. And the only possibility to decay is through the weak interaction into lighter leptons, okay? And the possibilities are indeed two. The charged pion, for instance, the pi minus, can decay either into electron and electron antineutrino or into muon and muon antineutrino, okay? And you see here the two diagrams, okay? So we have the first vertex is the same, is a U bar D, okay? Then we have the W, and then we have the second vertex, which is in one case is electron neutrino, in the other case is muon neutrino. Clearly, the pion can never decay into a tau lepton because the tau lepton is much heavier, so energy will not be conserved in the decay. So let's now compare these two decays. Now, assuming the universality, the Lepton universality, okay, so the universality of weak interaction for leptons, one would say that the coupling at this vertex here should be the same as the coupling at that vertex there, okay, assuming Lepton universality, which is the standard model, essentially, so assuming standard model. And then the other vertex is the same, okay, so from the point of view of the couplings, these two decays are equivalent, okay. What about the kinematics? Now, the mass of the electron is clearly much lighter than that of the, smaller than that of the muon, a factor of 200. So clearly, from the point of view of the kinematics of the free phase space available in the decay, there is much more phase space in the case of the electron than in the case of the muon. Okay, and this goes with the fifth power, according to the Sargent rule. Okay, so this means that from the kinematic point of view, the decay into electron is much more favorable. Okay, it has much wider phase space than the decay into muon. Is that clear? So the muon channel is kinematically suppressed with respect to the electron channel, although from the dynamics point of view, or from the couplings, they should be the same. Okay, so the only difference is due to kinematics. And so one would expect that the electron channel is the dominant. Okay. However, the opposite is observed. So it is observed that the pion decay into muon with a probability of 99.99%. So something unexpected based on simple arguments. And the reason for that, we actually already know. It is about the chiral nature of the charged current weak interruptions, as we discussed last time. So what is the point here? As we found last time, charged current weak interaction can only couple with left-handed fermions or right-handed antifermions. This is the only way. All other contribution corresponds to zero currents, as we showed in the blackboard last time. Okay. Now let's start from the neutrino. So neutrinos can only be being fermions can only couple with the W boson only if they are left-handed. And since they are massless, the chirality of the neutrino essentially coincides with the helicity of the neutrino. Okay, so a left-handed neutrino coincides almost to a negative helicity state, and a right-handed neutrino corresponds to, which does not exist, to a positive helicity state. So the antineutrino from the pi minus decay, this guy that you see here, or either the muon antineutrino or the electron antineutrino, is always produced with a positive helicity because it is a right-handed antifermion. Okay. And if you now look at the pi plus decay, in this case we have the neutrinos. So the neutrinos have to be left-handed, and so they are always produced with negative helicity. Okay, where positive helicity means that the spin is aligned with the momentum, negative it is anti-aligned. So let's now look into the decay. Okay, suppose we have in the center of mass of the pion, so the pion is at rest, is decaying. Okay, so we have a lepton neutrino back to back. So the spin of the pion is zero, right? It is a pseudo-scalar meson. So the spin in the final state must also be zero. Okay, otherwise we would have a violation of the angular momentum conservation. And the only way for the final state angular momentum to be zero is that the spin of the two particles are opposite. Okay, -1/2 +1/2. Total is zero, as in the initial state. But we know that the antineutrino has to be positive helicity, has to have a positive helicity because it is a right-hander. Okay, so the spin direction of the antineutrino is fixed by this. and it is parallel to that of to its momentum. And so the only possibility for the spin of the electron is that it is also aligned with the momentum. Okay, is that clear? So now this is indeed the crucial point, because due to this, the angular momentum conservation requirement, both leptons in the final state are produced with the positive helicity. That is fine for the antineutrino, because it is right-handed, and so it has to have a positive helicity. But it is not so good for the electron or for the muon, because they are fermions, and so they can only couple weakly if they are left-handed, and so one should expect here a negative helicity instead, right? So in other words, since the charged current-weak interaction is non-zero only for left-handed charged particles, the charged lepton, or either the electron or the muon in the decay, is produced with the wrong helicity. And if the electrons or the muons were massless, completely massless, then helicity coincides with chirality, so they would have been produced as right-handed fermions, which do not exist, cannot couple with weak interaction. So in that case, the pion could even not decay at all. Okay? It can decay because electron and muons are massive, and so the helicity does not exactly correspond to the chirality. Okay? So there is a small chance for the pion to decay due to the fact that both electrons and muons are massive. And the chance is much higher, now we understand, because the mass of the muon is much larger than the mass of the electron. So for massive particle, chiral states do not coincide with helicity states, and so the weak decay to a positive helicity lepton can still occur, although it is highly suppressed. Okay. So any positive helicity spinor can be also always decomposed into a right-handed chiral spinor and a left-handed chiral spinor. Okay. Now, of the two components, only the left-handed chiral component can interact weakly. Okay, to the charge current weak interaction. Okay, so essentially only this second term contributes to the matrix element. Okay. But then we have a suppression factor of 1 minus beta. What does it mean? This means that if your charged lepton is highly relativistic, so beta is close to 1, then this object is close to 0. Okay? If, on the other hand, your charged lepton is slow enough that beta is much smaller than 1, then you have some probability to occur. And this is in fact what happened between the electron and the muon. The electron produced in the decay is highly relativistic with a beta of 0.99997, and so this object is essentially 0, and that's why we don't observe the electron decay, although it is kinematically favored. For the muon, which is massive, more massive, the beta is only 0.27, and we do have some chance here to decay. Okay, so this is now hopefully understood why the pion can only decay essentially to the muon channel. Pion decays to electrons are strongly suppressed with respect to those of muons, despite being kinematically favored. And now the theory, if you use now the V minus A theory, you can compute exactly your prediction for the ratio of these two decays, right? And it turns out that it is indeed order of 10 to the minus 4. So the electron is something like suppressed by 1 part over 10,000. And this is in good agreement with the measured value. Okay, the measured value of this decay width is indeed of the same order, 1.2 10 to the minus 4. So all this is understood assuming the V minus A structure of the charged current weak current, right? We are assuming this because as a result of this, the W boson can only interact with the right-handed antiparticle or left-handed particles. Okay, if nature would have made a different choice, okay, suppose that the weak interaction would be either a scalar or a pseudo-scalar, then one expects this ratio here to be order of 5.5. So in complete disagreement with the experimental result. Okay, so the decay of the pion, the charged pion, is a strong, very strong proof of the V minus A structure of the charged currents. Okay, I hope I convinced you about this. Okay, is that clear so far? Okay. So far we treated essentially the charged weak interaction of leptons. Let's now see what happened to the quarks. And as usual, the golden process is the beta decay. So the neutron that goes into proton with the electron and antineutrino. Okay. The process is here represented at the quark level. So as we already discussed, the up quark, the first up quark is a spectator, doesn't do anything. The d quark also, and then the other d quark transformed into an up quark with emission of the W, which decays into electron and electron antineutrino. This is the beta decay of the neutron. And from the elementary point of view, we can just single out this interaction here at the elementary level. Okay, so we have a d quark that goes into u quark with emission of a W, which is the case into electron and electron antineutrino. Again, here we can identify two vertices with, in principle, two different couplings, as we did before for the Moon decay. So let's say a coupling with the quarks, so the W coupled with the quarks, and a coupling with the electron and the neutrino. And so we can write down essentially the cross section of these, or the decay rate, sorry, of the beta decay, which is proportional to the square of the matrix element, as proportional to these two couplings here. Okay, the electron vertex and the quark vertex. So keep this in mind. We will come back to these in 10 minutes. Now let's compare indeed this diagram. So again, the beta decay, the d into u with the plus electron antineutrino decay, with the Moon decay that we just studied before. Okay, so let's compare these two processes, elementary processes. Of course, the second vertex is common, is the same. So the coupling here must be the same as the coupling there. It's just the W goes into electron and neutrino. The upper vertex, in principle, could be different because we have a Moon vertex and a quark vertex. Or it will be the same in case the universality can be extended also to the quark sector. Okay, so we know it holds for the lepton sector, but if it also holds for the quark sector, then we should expect the same coupling here and there. Okay. So for the leptons, we know that the universality holds, but now when looking at the experimental values, we found that this is not true when comparing quarks to leptons. So in other words, the coupling at the UD vertex is found to be 5% smaller than that of the Moon vertex. And you see here the two values. Okay, you can compare them. And there are situations where the difference is even higher. Okay, let's compare, for instance, the K minus decay into Moon with the pi minus decay into Moon. In one case, we have a U bar S quark content. In the other case, we have a U bar D quark content. And in this case, if you compare now the coupling at the quark vertex, so GUD with GUS, then they differ by a factor of 20. So one observe here a huge violation of the universality. Or in other words, universality holds for leptons, but not for quarks. So the experimental evidence seems to support that there is no universality of the weak coupling to the quark sector. Okay. Now this was a bit disturbing at the time, and Nicola Cabibbo in 1963 provided a solution to this. Okay. So the solution to this puzzle was provided in 1963 when only 3 quarks were assumed. Okay, so we are essentially in the period of the quark model, okay, by Gell-Mann and Zweig. So only up, down, and strange quarks were supposed to exist at that time. So according to Cabibbo hypothesis, the weak interaction of quarks have indeed the same strength as for leptons. So according to Cabibbo, there indeed exists a unique, universal Fermi coupling. So why do we observe a different coupling now in the quark sector? The explanation for this, according to Cabibbo, is that the weak eigenstate of quarks differ from their mass eigenstates. What does it mean? This means that the quarks that participate to the weak interaction are not up, down, and strange, which are the mass eigenstates or flavor eigenstates, but rather different states, which are weak eigenstates, so eigenstate of the weak Hamiltonian, if you like, which can be obtained as combinations of the mass eigenstates. So let me go to this. The quarks that participate to the weak interactions are not the flavor or mass eigenstate UDS, but specific linear combinations of them. So this is, we are introducing here the so-called quark mixing. Let's look at this into more detail. So in particular, the down type weak quark eigenstates that we call now D prime and S prime, so these are the ones that participate to the weak interaction, okay? They do not coincide with the flavor states D and S, but can be obtained in a combination through a specific rotation matrix. So they are essentially rotated eigenstates with respect to the flavor eigenstates. This rotation matrix is provided here is a 2x2 rotation matrix, which depends on only one single parameter, which is this angle that is known as the Cabibbo angle. So when you now consider the product of the matrix with the vector, you obtain these two combinations for the weak eigenstates. So the D prime is a combination of the D and S, so the cos and the sine of the theta Cabibbo, and the S prime is this different combination of the D and the S. Okay? So what really takes part to the weak interaction is not D and S, but it is D prime and S prime. It is a quantum superposition of eigenstates. Okay? Like the Schrödinger cat into the box, if you like. What about this mixing angle? The mixing angle, or the Cabibbo angle, has been measured by comparing lifetimes and branching ratio of semi-leptonic and hadronic decays. Okay, and today we have a rather precise value, which is order of 0.22 radians, that corresponds to approximately 13 degrees. But it is the level of mixing between the quarks. Okay, this tells you how quarks are mixed. And so the sine of the theta Cabibbo is 0.22, and the cosine is 0.97. So having said that, okay, we can now arrange the quark weak eigenstates, so those that indeed participate in the weak interaction, in the form of a doublet, in the same way we implicitly did already for the leptons. For the leptons, we have electron, neutrino, muon, neutrino, tau, neutrino, and then for the quark we have U, D prime. Okay. Where D prime is this combination. So these are the two weak eigenstates of the first two up and down. Okay. And once you arrange now your quark, your up, down, and strange flavor quark into a U D prime weak doublet, then you obtain the same exact coupling of the leptons. Okay. So once you consider that it is not the D, but the D prime that is interacting weakly, so with also a component of the S, then it turns out that the coupling for the quark is exactly the same as that for the leptons. And so it is universal for both quarks and leptons. Let's see how this works in a more clear way. First of all, let me show you that. So why have we not rotated the up quark and we only rotated the D and the S? This is a convention. Okay, we could have chosen the opposite convention, but the convention is that only the down type quarks are rotated, okay? And the up type, so up, charm, and top remain unrotated. So let's see what happened. So we have here an elementary vertex where the W goes into U D prime, okay? And in this case, the coupling is indeed G, the same as for leptons. But this, due to the quark mixing, we can decouple into two contributions. The W that goes into UD, but now with a different coupling, which is the GUD, which contains the cosine of theta Cabibbo, so it is a bit smaller than G, plus the GUS, okay, which now includes the sine of theta Cabibbo, and it is much smaller, okay. So in other words, the apparent difference between the coupling constant is due to the quark mixing phenomenon, which arises from the fact that the quark eigenstate of the weak interactions are mixtures of the quark mass eigenstates. Okay? The coupling is universal. Let's now go back to the beta decay, okay, the one that I showed you 4 slides ago, okay. So we have now our matrix element that we write as proportional to the 2 coupling at the 2 vertex, the electron vertex and the UD vertex. Now, for the electron vertex, the Fermi coupling is just the square of the lepton vertex, lepton coupling. And the quark coupling, now UD, we know that we have to multiply this by the cosine of theta K, okay? And so at the end, the matrix element is not G to the 4, but it is G to the 4 times cos square of theta C. And this is why we observe this difference in the coupling. Let me show you 3 relevant examples. Okay. So the first one is, as usual, the decay of the muon. Okay, the muon going to muon neutrino, and then the W decays into electron and neutrino. In this case, we have 2 vertices, both leptonic. There is no mixing, and so the matrix element is proportional to G squared. Let's consider again the beta decay. Okay, now we have the D quark into U quark that goes into W and then electron and positron. So we have a quark vertex, okay, which has to be corrected by the cosine of theta C times a pure leptonic vertex which comes with G. So the matrix element is G squared times cosine theta C. And then we have a pure hadronic process, okay, the lambda 0 into proton pion. Now in this case we have 2 quark vertices. One is S into U, so it goes with the sine of theta Cabibbo. The other is UD, so it goes with the cosine. And so the matrix element is proportional to G squared corrected by cos theta C times sine theta C. Okay. And I told you a few slides ago that there are also more extreme cases where the different coupling is order of 20, if you remember, up of 20. So let's now consider these in the light of what we learned about the Quark mixing. So different coupling standards are found for the UD and the US weak charge current vertices. In particular, the question, if you remember, was the decay of the Ckm into muon and the pion into muon, okay, where the coupling is observed to vary by factor of 20. So now we can understand this in terms of the Quark mixing, okay? So this is the pion into muon neutrino and the Ckm into muon neutrino. The second vertex is the same, is a pure leptonic, so here we have just a contribution of G. The first vertex is different because we have a UD here and a US there. So in one case we have to correct by the cosine of theta Cabibbo, in the other by the sine of theta Cabibbo. And so you can now measure the ratio of these 2 decay widths, okay? This goes like the ratio of these 2 couplings, okay? That you have to correct properly with the cosine and sine of theta Cabibbo. So this is essentially proportional to the tangent square of theta Cabibbo, that is indeed the factor of 20. Okay? So in other words, thanks to this brilliant idea by Nicola Cabibbo of the Quark mixing, we have now a clear understanding of how the charged current coupling goes to both quarks and leptons. The coupling is indeed universal for everything. The only thing is that quarks mix themselves because the flavor eigenstate do not coincide with the weak eigenstate, but they are combination. Now, so the Cabibbo mechanism appeared to solve this problem, but it left another problem open. So although the Cabibbo mechanism solved the apparent lack of universality of the weak interaction in the Quark sector, there was still some unexplained experimental parts. So let's see what this is about. So while the Cabibbo model, in principle, allowed for weak neutral current processes with change of strangeness, so with delta S equal 1, the processes were not observed in nature, okay, or found to be extremely suppressed, to be more precise. Okay. So let me take you an example. Okay, so here we have 2 different processes. One is the K plus into pi 0 muon, and the other is the K plus into pi plus and then neutrinos. Okay. And you see here the 2 corresponding diagrams, okay? So the first diagram is mediated by a charged current with the exchange of a W boson. The second is mediated by a neutral current with the exchange of a Z boson that we will study next. Okay. In both cases, we have a change in strangeness by 1 unit. Okay. We have a strange quark in the initial state, and we don't have in the prime state in both cases. Now, the question is that the first one is observed in nature, the second is not observed in nature, although it is admitted by the Cabibbo theory. And indeed, if you measure now the ratio of the two branching ratio, we found that the first one, the second one, so the neutral current one with the flavor changing is suppressed by 7 order of magnitudes. Okay. And this problem can be actually generalized to any flavor changing neutral current decays. In this case, it was a strange changing, but it can also be any other flavor. If a charged current process requires a change of flavor, delta S, delta C, delta B, whatever, then it is not observed. Actually, it is observed to be highly suppressed. Okay, and this could not be understood in the framework of the Cabibbo hypothesis. So the solution to this was proposed a few years later. We are now in 1970 by these three guys, Glejo, Iliopoulos, and Luciano Maiani, who provide a new mechanism that is called the Ckm mechanism by the initials of these three gentlemen. And the core of the problem is the following. So when the Cabibbo mixing was proposed, as I was mentioning, only 3 quark types were known: the up, the down, and the strange. Okay, we were in the epoch of the early quark model by Zweig and Gellner. Now, according to the Ckm mechanism, a 4th quark must exist in order to solve the problem of the strangeness and neutral current processes, which has to be coupled with the S prime weak eigenstate. So according to their prediction, the new quark that they call the charm, as you know, have to have the following quantum numbers. So the charge is fractional, 0 isospin, 0 strangeness, and the charm +1. And the important point, the crucial point, is that it has to form a second quark doublet together with the S prime weak eigenstate. Okay. So you can have 2 different weak quark doublets only if you allow for the existence of an additional quark, the charm. That was not even predicted up to now. This was the only theoretical argument to ask for a new quark, okay, the charm quark. So let's see now how the addition of a 4th quark and so of a second weak quark doublet can solve the problem of flavor changing neutral current processes. Okay. So first of all, let me anticipate something that we will study next week, and so the shape of the current for neutral current processes. So for neutral current, as we study, this is proportional to EL 2L gamma 2L plus ER 2R gamma 1. So this we will study next. Okay, so don't worry for the moment. Just consider these are left-handed chiral states for quarks. These are right-handed chiral states, and these are the 2 different couplings, neutral current couplings for the left and the right. Okay, this will come back later next week. For now, just what is important is that the shape of the current is of the type Q bar gamma naught. Where Q denotes a member of a quark doublet, weak doublet. So let's first of all consider the status before the Ckm mechanism. So the status according to Cabibbo. So according to Cabibbo, we only have 1 quark doublet, because we have only 3 quarks available. So it's the U, and then we have the missing, so it's D cosine theta C plus S sine. And so our network current for only 3 quarks, the up, the down, and the strength of the variable, be proportional to something like u bar gamma mu u plus d prime bar gamma mu. Okay, so we have to repeat if for the 2 members of the doublet. Okay, so we have these 2 contributions. Okay. So the first one remains the same, u bar gamma mu u. And the second, we can now expand, taking into account that the d prime is given by this combination here. So we have d prime, d bar cosine theta bimbo plus s prime sine theta bimbo gamma mu, and then we have the same here, d cosine theta bimbo plus s sine theta bimbo. Okay, we are just substituting these expressions here and here. Okay, now let's go on. So we have u bar gamma mu u plus. Now let's take the product. So we have a cos square theta c that multiplies the d bar gamma mu u plus sine square theta c that multiplies s bar gamma mu s. And then we have the mixed terms. So we have plus, that we go here, plus cosine theta c, sine theta c, d bar gamma mu s, plus sine theta c, cosine theta c, s bar gamma mu b. Okay. So let me continue here. So we have, in other words, u bar gamma mu u plus, and we have the pure terms, so the cos square theta c d bar gamma mu d plus sine square theta c s bar gamma mu s. And then we have plus sine theta c cosine theta c. And then we have the d bar gamma mu s plus s bar, no, sorry, gamma mu b. Okay. Now let's consider these pure members here. Okay. In this case, we have the x over b. Okay. There is no variation in strangeness. And in this case here, instead, we have the x equal to Lepton. Okay, so this is indeed, these are the processes that are allowed in nature, so that are observed experimentally, but these are not. Okay, so the Cabino theory, as I was mentioning, allows for something that is not observed in nature. Okay, let's now work out the example after the G mechanism, so allowing for a second for doublet. So now we have, okay, clear. Two of doublets, u d prime, that is the same as before, that is u d cosine theta c plus s sine theta c. And then we also have the other of doublet, that is the c s prime is C, and then we have S cosine theta C minus D sine theta C. Okay, and let's now repeat our computation, but now including 4 quarks, up, down, bend, and so on. This is proportional to U bar gamma U, gamma mu U, plus D prime gamma mu D prime, plus C gamma mu C bar gamma mu C, plus S prime gamma mu S prime. Okay. Now, the first two we've already computed before, so let me just call these as J and C to the S. So this is J and C to the S plus C bar gamma mu C plus, and now we have to work out this way. This way here, where we have to substitute this combination here and there. So this is S cosine theta C minus D plus D bar sine theta C, and again S cosine theta C minus D sine theta C. So, okay, let's do the product of before. So this will just copy U D S plus C bar gamma mu C plus, and now we have cosine square theta C S bar gamma mu S plus sine square theta C D bar gamma mu D, which are the pure terms. And then we have the mixed terms minus cosine theta C sine theta C D bar gamma mu S plus S bar gamma mu D. Okay. Let's now make use of the expression that we derived before. So let's put now everything together. So once it is so, this is U bar gamma mu U plus cos square theta C plus sine square theta C D bar gamma mu D plus sine square theta C plus cos square theta C S bar gamma mu S plus C bar gamma mu C plus the mixed terms sine theta C cosine theta C D bar gamma mu S plus S bar gamma mu minus sine theta C cosine theta C D bar gamma mu S plus S bar gamma mu D. And now you see the magic. Okay, so this is 1, this is 1, and those two, the nasty terms, cancel. Okay, so these are those that correspond to a change of signness. So they disappear now as soon as you allow for 2 quark doublets. Okay, so overall, what is found is that when we have 4 quarks, then you are essentially left with only pure terms. So U bar gamma mod U plus B bar gamma mod B plus S bar gamma mod S plus C bar gamma mod C. And all these guys do not have a change in strangeness. And so this is a grid that consisted with observations. Okay. Now, of course, the theory was fantastic, but it needed to be proved experimentally, and the expected proof was the existence of the charm quark. Okay. And if you remember, the charm quark was discovered 4 years later, in 1974, with the discovery of the Jet-Psi resonance in 2 different experiments. Okay, the Slat and Brookhaven. That was the first observation of a CC bar state, so the first experimental proof of the existence of the fourth quark. And this, of course, constitutes the smoking gun for the Ckm mechanism prediction. Okay. Now, is flavor-changing neutral current process absolutely forbidden in the standard model? No, it is. They are possible, although not at free level, so not at first order. At first order, they are killed by the Ckm mechanism. Okay, but they can occur at higher order, so with more complex diagrams. And in particular, there is a set of diagrams which are called the Pendulum Diagrams, as you see here, which allow for flavor-changing neutral currents. Okay, so for instance, here we have a D a certain quark that goes into a S a certain quark. Okay, so whatever happens in between, we have a D quark that goes into an S quark. So it is a neutral current because the electric charge of the D is the same of the electric charge of the S. And it is flavor changing because we have no strangeness in the initial state and we have a strange quark in the final state. So this is a clear example of flavor changing neutral current process. Okay, so this cannot occur indeed at free level, but only through these more complicated penguin diagrams. Okay, where essentially a W is extended here. Then we have a loop of up-type quarks, so U, C, or T, and then we have at the end a gluon that correlates these with the spectator quark. Okay, so it is possible, but it cannot in the standard model, but can only occur through more complex diagram. And since we have now more vertices, this is of course a much less probable process. Or in other words, it is possible but suppressed. Okay. Ok, facciamo un break. Riprendiamo dove so. Siamo un quarto? Siamo 10 minuti di pausa. Ok, so we recombine at 15 past 10. Any questions? Okay. Okay, we can recombine, restart. Okay. So still on the Cabibbo mixing, okay, just a few additional comments, and then we will try to solve some exercise. So let's consider now semi-leptonic process that involve charm quarks, okay? We have essentially two possibilities, okay, within the still Cabibbo theory enlarged with the G mechanism. So the C can go into an S quark, okay, and then we have some other leptonic vertex, or the C can go into a D quark. And as we know, this corresponds to the same fundamental coupling, but with different strength due to the cosine sign of the Cabibbo angle. So let's first consider the C into D, so the C into S. So, mi sentite? Mi sentite da casa?
Sì.
Okay. Perché ho chiuso il microfono, poi l'ho riaperto. Okay, so let's consider the transition between the charm into strange, first of all, okay? So it is proportional to the two couplings, GCS, and then we have the G electron, the electronic one. So for the electron, this is just pure the G coupling, and then for the GCS, it is G cos theta Cabibbo, okay? So overall, this is proportional to the Fermi constant, and then the cosine, and so 0.97 times the Fermi constant. And then when you calculate now the decay rate, you have to square these, and so at the end you get 0.95 times the squared Fermi constant. What about now the transition of a charm quark into a D, okay, CD? So the leptonic vertex is the same, but now the transition involves a sign of the theta Cabibbo, okay? So at the end, the sign first, being a small angle, it is a small quantity as well. So at the end, it is 0.22 GF. And so when you now square these, you obtain a very small probability, 0.05 times square, compared to the previous one. So the quark transition within the same family, so either up into down or strange into charm, these are said to be Cabibbo favored, whereas the quark transition between the first and the second family, so charm into down or strange into up, are suppressed by a factor sine square divided by cos square, okay, as we saw here, and these are called Cabibbo suppressed. Okay, so let's now solve some simple exercise. So the first one is, say, which decay is, oh, sorry, let me, okay, all right, one moment. I'm still sharing, right? Yes. So say which decay is suppressed between the tau plus into k plus antineutrino tau and the tau plus into pi plus antineutrino tau. So let's go down now the decay of the tau plus. Sorry, this is an antiparticle, so the arrow should point backward in time. So this goes into an anti-neutrino with the emission of a W plus. The W plus then goes into a U vector. That is A plus. Okay, so this is the tau plus into the P plus. Sono sicuro che ho fatto lo sharing qui. Da casa vedete la lavagna?
Sì, vediamo.
Okay, so we have two couplings here. Okay, so this is the electronic one, G tau nu, and this is the quark one, G US. So the matrix element will be proportional to G tau nu times G US. And so this is G times G sine of theta Cabibbo. that is proportional to GF sine theta capital, that means 0.20 GF. So when we now square this, and it turns out to be 0.05 df squared. And so this is a big expressed. Let's now consider the decay into a pi plus. So the difference that is now a d bar. And all the rest is the same. So this is a u. So in this case, and fi is proportional to g tau mu times g d. That is g times g cosine of theta c. That is proportional to gf cosine of theta c. That is 0.97. Yeah. Then take the square. And this turns out to be 0.95 squared, and so this is a big farad. Okay, very quickly, let's solve two other similar problems. Well, the second one is say which decay is suppressed between the C minus in lambda z pi minus and for the decay the lambda plus pi.
There seems to be a problem with the camera. It's all blurred. I don't know what. I think it's lost focus.
Vedete gli altri ragazzi di casa, riuscite a vedere bene?
It's back. Thank you.
Maybe your connection, I don't know.
Maybe it was my connection. Yeah.
Okay. So lambda 0, and then we have 2 plus and neutrino. So let's start drawing the first diagram. So let's see, if you remember, is a doubly strand barrier with an SD object. The lambda is a UDS. What happens is that this is spectator, this spectator, this changes in the quarter with the emission of W minus, which decays into a D theta, which makes our findings. So the couplings, here we have a GSU, and here we have a GUD. So we got size GSU times GUD, that is G sine theta C times G sine theta C, that is GF sine theta C times cosine theta C, that is approximately 0.22 GF. And so the decay width is proportional to the square of the matrix element. It will be proportional to the Fermi coupling squared, and then we have sine theta C squared times the cosine theta C squared. This is 0.048 G squared. So this is the bimbo at rest. Let me now draw the other one. So the lambda C plus. So this is a C D U object variant. And because we get on here, it is S D U. So again, the upward catheter, the equal catheter, and now we have a transition between the trunk quark and the strange quark. So it is mediated by a W plus that goes into a mu plus and a mu neutrino. So we have nothing G, yes, G, mu. So this is CS, there is the same family, right? The second family. So this is just G cosine theta C times G. So this is GF cosine theta C. It is 0.97 GF. And we take the square of this. It is square of this, so it's GF squared times the cosine square of theta bimbo. It is 0.95 GF squared, and it is our bimbo flower. Together. That's the problem. So the third problem is draw the Feynman diagrams of the following hadronic weak decays and estimate the relative decay rates. So the decays are the D0 meson into A minus A plus, the D0 meson into Phi plus Phi minus, and the D0 meson into K plus Phi minus. Okay, so let's start with the first one. So the D0 is a U bar C. And then we can form a pi and the Ckm. So A minus is a U bar S. So this is the vector, and this transforming the next one is the elimination of that plus that goes into that U B bar that forms the pi plus. So the couplings G US G UD, so they are now both quark couplings. And so and Fi is proportional to G CS and G UD. They are both transition within the same family. So within the second family and within the first family. So they are both favored, right? So this is G cosine theta bimbo times G cosine theta bimbo. So this is proportional to G F cos square theta bimbo. And so this is 0.95 GF. And then when you calculate the square of this is 0.90. Yeah, this is a capable average. Now the second, 0. Okay. See? Now this goes into 2 piles. So this is U bar into U bar, and this goes into E. Then with the addition of the plus that goes into the D bar, forming the pipelets. So couplings G CD and G CD. Now, the first of the two is a transition between two different families, so this has to be suppressed. G sin C. The second is a transition within quarks in the same family, so this is favored. So with the cosine. GF sin theta, cosine theta. So this is at the end 0.22 GF. When you calculate now the square of the matrix element, you obtain something like 0.05 GF squared. So this is a window suppressed. Now the last one. So now we go into a K plus or minus. C minus B. Right? So with that plus that goes into a H bar, okay, forming the K plus. And now couplings G PD G US. Now in both cases we have a transition between quarks of different families, so they are both suppressed, right? So this is G sin theta C times G sin theta C, that is proportional to GF sin square theta C, which is of the order of 0.05 GF. And when you take now the square of this matrix element, is of the order of 0.003 GF squared. This is called the Cabibbo doubly suppressed. It is suppressed twice. So we're just comparing this. Okay, so we can also, okay, let me write down now the direction of this decay mix. So by just comparing the first and the second, we will say, okay, we're just changing K plus and K minus, K plus and K minus, but it makes a huge difference. Okay? All right. Okay, so far we have considered the case of up-down charge strand, but we know that there is an additional family, okay, the heaviest quarks, the bottom and the top. So we have to expand this quark mixing structure to include all the 3 quark families. And this is done through the so-called Kabibbo-Kobayashi-Maskawa matrix, okay? So it is a generalization of the Kabibbo rotation, but now including all 3 families. So the Kabibbo mechanism is naturally extended to the 3 generation of quarks by replacing the 2x2 Kabibbo matrix with a 3x3 unitary matrix, which is known as the Ckm matrix. Okay, so here we have the 3 weak down quark type eigenstates, d prime, x prime, b prime. Here have the corresponding unrotated eigenstates, so the mass eigenstate, and in between we have this 3x3 rotation matrix. Now, when calculating the current, we have of course to include here the probability, which depends on the different combination of the different transition between quark families. Okay, so essentially we have to put into our vertex factor the proper matrix element of the Ckm matrix. So consider, for instance, this vertex here, D into U with emission of W. Okay, in this case, we know that you have the adjoint spinor for the U, then we have at the end the spinor for the D, in between you have the vertex factor, and within that we have to put the UD, the VUD matrix element, so this one, this guy here, okay, in order to take into account properly the different coupling, the non-universal coupling, but it is universal. What about the opposite process? Now it is now a U into D. So the difference is now that the down quark is now adjoint, before it was not adjoint. And if this happens, then in this case, you have to take the complex conjugate of this Ckm matrix element, so BUD star. Okay, formally. Now, let's be general, okay? In general, an n by n rotation matrix has a number of real parameters given by n times n minus 1 divided by 2, okay? And this we call the Euler angle in this hyperspace, and a number of phase angle given by this quantity here, n minus 1 times n minus 2 divided by 2. So let's consider the case of the Kabibbo matrix. Kabibbo matrix is a 2x2 rotation matrix, so n is equal to 2. And so the number of real parameters at the end is just 1. In fact, we have only one parameter, which is the Kabibbo angle. What about phase angles? If you apply this formula here with n equal to 2, you get 0. We don't have any phase angle, just one real parameter. Let's now consider the Ckm matrix. It is a 3x3, so now n is equal to 3. And so in this case, you obtain 3 independent real parameters that we can call the θ12, θ23, θ13, which are the mixing angle for first, second family, second, third family, and first, third family. And then when you calculate the phase angle, you obtain now 1. Okay? So overall, the Ckm matrix, for the fact that it is a 3x3 rotation matrix, it includes 3 real angles, the Euler angle, so 3 real parameters, and 1 complex phase. Now, we can decompose the Ckm matrix in a proper way. Let me just, for shortness, write Sij as the sine of θij and Cij as the cosine of θij, okay? And so we can decompose the Ckm matrix into these 3 blocks, 3 3x3 matrices, or we can express it all together, okay, in terms of all these 3 real parameters and the delta complex phase, okay? So this is the full picture of the Ckm matrix in terms of the cosine of θ12, θ13, θ23, and the delta phase. Now, the first, the block, the 2x2 block that you see here in the last piece is exactly the Kabibbo matrix. So the Kabibbo matrix is, of course, a part of the Ckm matrix, okay? And so the C12, or the θ12, of course, it is just the Kabibbo angle, coincides with the Kabibbo angle, okay? What about the other 2 angles? Those angles have been also measured, okay, but they are much smaller. So the Kabibbo angle, or θ12, is 13 degrees, but now the θ23 is 2.3 degrees, and the θ13 is even smaller, 0.2 degrees, okay? So for instance, if we take now the first element of the Ckm matrix, the VUD, okay, which is given by cosine θ12 times cosine θ13, okay. The cosine θ13 is essentially 1 because the angle is extremely small. So at the end, this corresponds to the cosine θ12, which is the cosine of theta B, okay. So indeed, the VUD is just the cosine of theta B. What about this complex phase delta? So this is actually extremely important, as we will study next week, because the presence of this complex phase is the reason why weak interaction violates CP, so simultaneously charge conjugation and parity. So CP violation only arises due to this delta phase. And as we will study next week, at the time of the G mechanism, there was no need for an additional quark family. Okay, with 4 quarks, you can explain everything at that time. Okay, the reason for testing for a new family of quarks, the bottom, the top, was just due to this problem here, because people was observing CP violation, and the only way to encode CP violation in the standard model was allowing for a 3x3 matrix, mixing matrix, and so allowing for a third family of quarks. Okay, we will come back to this. So the matrix element of the Ckm matrix have been measured, okay, from a large number of decays, and we know today quite precisely, although not all of them with the same level of precision. But one can also use constraints due to the fact that this matrix is unitarity. So once you apply the constraints due to the unitarity, you can get information where the experimental data is lacking or is less precise. So putting together information from the experiments and applying also unitarity constraints, at the end, these are the values of the 9 Ckm matrix elements. Okay. So what we can learn from here, first of all, the smallness of θ23 and θ13 leads to a near diagonal form of the Ckm matrix. If you look at the matrix, essentially the diagonal terms are very close to 1, okay, and the non-diagonal are close to 0. So due to the smallness of θ23 and θ13, the Ckm matrix is almost a diagonal matrix. The diagonal elements describe the transition within the same family. So UD, first family, CS, second family, top-bottom, third family. Okay, and this is why they are so large. And deviate from unity only by 2%. Now, the values VCB and VTS, which allow for transition between the third and the second family, okay, these are nearly 1 order of magnitude smaller than the transition between the second and the first family. Okay. So according to the transition from the third to the second family, so top into strands and bottom into charge are suppressed by nearly 2 order of magnitude compared to transition from the second to the first family. And finally, this is, of course, in a higher degree when considering transition from the 2 opposite families, from the third family to the first family, so top into down or bottom into up. These are extremely suppressed, and this is why you get these such small values in the matrix element, in the Ckm matrix. This can be also represented in this way, right? So the transition between the same family are the most probable. It corresponds to the diagonal elements. These are favored. Then we have those between families which are close to each other, second to third, or first to second, and these are suppressed. And then we have the extreme case, the transition between the first and the third family, which are highly suppressed. Okay, one more and last exercise. Now about the Ckm. So draw the Feynman diagrams of the following electronic decays and estimate the relative amplitudes for the B plus into the 0 bar pi plus, BS0 into B sub S plus pi minus, and lambda B into lambda C pi minus. Okay, let's start with the first one. So it is a B plus into B0 bar particles. So the B plus meson is a U B bar meson. The B0 bar is a U C bar meson. So it is spectator. This transforms with emission of a W plus that goes into a particle plus, so a U B bar. Now, let's consider the couplings. So here we have a transition between the third and the second family. So this is the GBC, and here the usual GUD. So the matrix element proportional to GBC times GUD. So this is proportional to G and the BCB matrix element of the Ckm matrix times GVUD. Now we can express this in terms of the sine and the cosine of the three mixing angles. So this is F, and then we have the sine of theta 2, 3 times the cosine of theta 1, 3, and the cosine of theta 1, 2 times the cosine of theta 1, 3. You can check yourself into the Ckm matrix. So what we have here, the F sine theta 2, 3 times cosine theta 1, 2 times cosine squared theta 1, 2. It is the F sine of 2.3 degrees times the cosine of 13 degrees times the cosine squared of 0.2 degrees. And it is, at the end, 0.039 yes. Let's now work out the second one. So the B, the second is the P0S bar going into a BS plus times phi minus. So the B0S bar is the S bar B object. And we have the T meson S bar plus then S bar C. On this spectator, we have the transition with the emission of W minus that goes into where the form phi minus, so it must be a bar. So you are. So the couplings GBC, GUD. Okay. We have a transition between the third and the second, and then yes. So this is proportional to G, BCB times GVUD. Okay. So despite the decay is different, is a different decay than before, the couplings are the same as the previous example. Okay, so we don't have to work out again. So the end result is the same. This is 0.039. Yeah. Okay. The couplings are the same as before. And now the last one. Sorry, the last is around 0 T. that goes into a lambda 2 analysis. So this is the variable, so it is a U D B that goes into lambda C. Lambda C. It is a UDC. Spectator, we have a W matrix that goes into a U bar. Nice. Let's have a look at the coupling. And again, we have GDC and D. Okay. So also in this case, it will be the same. So three very different decays, but essentially the probability is the same because it is driven by the same couplings. So one can also write that the decay rate of A is the decay rate of B is the decay rate of C as 100 takes 2. Clearly, the phase space will be different, okay? So at the end, will be different from kinematical point of view. That's why I'm using a proportional here, okay? But from the dynamics point of view, they are equivalent. Now, last few words about the Ckm matrix. Okay, so because of the near diagonal nature of the Ckm, it is convenient to express this matrix as an expansion in the relatively small parameter sine of theta 1, 2, that is order of 0.22. So one can make an expansion of this object into first order terms and then higher order terms, okay, that we can neglect. And at first order term, in this so-called Wolfenstein parameterization, the Ckm matrix looks like this. Okay, so of course we still have a dependence on 4 parameters. 3 are real and 1 is complex. This we cannot avoid, of course. It is the intrinsic nature of the Ckm. But they are now it is now shaped differently and also in a way that is also easier to measure experimentally. So the values of these the 4 parameters are given here, which are based on experimental measurements. Okay, so the lambda, rho, and A are real, and the eta is complex. And as we will see next week, CP violation in the quark sector requires this eta parameter to be non-zero, and in fact it is significantly different than 0. Okay. So the non-vanishing value of eta, which is related to the complex phase delta that I was mentioning before, is the only source of CP violation in the standard model. Okay, essentially, and it only occurs in the quark level. For the lepton sector, I will show you next week that there are hints, small hints, based on new results on the CP violation in the lepton sector, but in the sector of neutrino physics, which we will discuss next week. Okay? For the moment, the only, let's say, official source of CP violation in the standard model is this one, okay? And it is related to the non-zero value of this eta parameter here. Now, as I told you before, the Ckm matrix is a unitary matrix, okay? So we can write down constraints to the matrix element, just because it has to be unitary. And you see here 3 equations that you can write here to enforce the unitarity, which of course constrain different Ckm matrix elements. And we can represent these also geometrically, okay? So the fact that the sum of these 3 quantities must be equal to 1 is equivalent to say that the sum of the internal angles of a triangle must be 180 degrees. So we can make this kind of parallelism. And so we can represent our essentially Ckm matrix in the complex plane in a triangle, which is called the unitary triangle, unitarity triangle. So these unitarity relations are actually translated into different unitarity triangles. This one is the one that is most used. So we are now in a complex plane where rho is a real parameter and eta, as I told you before, is a complex parameter. Okay. And so depending on the value of these rho and eta that I showed before, okay, the shape of the triangle will be different, and so the angle of the triangle will be different, the alpha, beta, and gamma angle. These angles can be inferred experimentally by measuring different kind of processes. You see some examples listed here, and the sides of this triangle are related to proper combination of the Ckm matrix elements. Okay. So if eta would be 0, okay, then geometrically the triangle would flatten down to the real axis, right? And this would correspond to having no CP violation. Okay, because CP violation only relies on this eta parameter being non-zero. Okay. So since eta is different than 0, then the angles gamma, alpha, beta, and gamma are sizable. They have been measured. We will come back to this next week. And indeed, the CP is violated. Okay. Okay, we can stop here. Okay. If there are questions, otherwise we see tomorrow at 11.